Okay, we're going to continue our lecture, okay, to the paper of Danzig, okay, here, okay, from the last clip, okay. We end up starting talking about the example of uh, two-stage linear programming model, okay. And one problem that Danzig referred to as a first example is this one, the minimum expected cost diet. Okay, this is one of the early application of linear programming. Okay, uh, initiated by a Nobel Prize agricultural economist. Okay, George Stigler. Okay, and he formulated the problem of finding the optimal feed mix. Okay, in order to satisfy the nutrient requirement. Okay, with uh, finding the right allocation among the ingredients, okay, in order to achieve the minimum cost diet. Okay, in this problem, Danzig identified the uncertainty at the price per unit of the ingredient. Okay, that is normally sometime the value in advance, or you know that they maintain a constant value for a while before the uncertain market, okay, force the situation to change the cost per unit. And he just gave this example, okay, and link this to the classic general formulation based on these three equations. Okay, the second equation is the what we call the cost of the diet, is the objective function, where P sub j in the equation represent the cost per unit for ingredient J, and X sub j is the amount in the optimal feed mix of ingredient J. Okay, and he identified the parameter A sub I j is the amount of nutrient number I, okay, uh, contained in a unit quantities of ingredient of food J. Okay, and Bi is the minimum quantity required for that nutrient number I. Okay, suppose that we have m nutrient. In this case, he didn't talk any uncertainty that can happen within A sub I j and B sub I here. He focused only the uncertainty for the cost of P sub j. Okay, and since we say that suppose P sub j have some uncertainty, and those uncertainty can be represented as the scenario or alternative. Okay, yeah, this is from the classic expected value. Okay, with X sub j as a constant uh, value, okay, identified by the decision maker that about the optimum mix, okay, or the a feasible mix that will satisfy this constraint. Okay, so when the randomness of P sub j, okay, and it's in the summation form, once X sub j was decision was made, it's easy by using the property of the expected value function. Okay, the expected value of C. Look at the notation that Danzig here. He used the capital C, okay, instead of the Z. Okay, the C su set, or in whatever you call it. Okay, this one is the objective function expected capital C. Only replace P sub j by their expectation. Okay, that would make it very easy to handle the uncertainty of the cost of objective function. And with the uncertainty of cost objective function, it has no relationship with the direct relationship with uncertainty of A sub I j and B sub I. Since A sub I j and B sub I is in the constraint in equation inequality number one, okay, the uncertain of A sub I j and the uncertain value of B sub I are correlated, okay, within the same I. Okay, but uncertainty of P sub j Okay, he over here is have nothing to do with these two. Okay, so in this case, once x sub j decision was made, okay, the expectation just replacing p sub j by its expectation. Okay, one you see that here is the x sub j are chosen before the price are known because it's uncertain condition. You don't know what is the exact of p sub j, but you can estimate the uncertainty of p sub j in advance by representing each j as a set of finite or infinite alternative, and then you using the probability theory find the expected value of p sub j. So that this example taking care the uncertainty of the cost coefficient of the objective function. And now we go back to the original metric model that we made it here. Okay. Okay. From the last clip, I did say that it make the problem more complicated with the uncertain of C. Since we have either finite or infinite alternative of C, the element within the vector C here, okay? It lead to the infinite, if with infinite alternative of coefficient of C trans within C transpose, lead to the infinite number of Z objective function C, okay? But with all of this, okay, since the uncertain of C have no direct relation related to A and B here, okay, so we can replace C here if we don't know the exact value by using their expected value based upon the linear relationship of the function of random variable. In this case, each element in the C vector is a random variable. Okay, and you might ask, what happened to U and V? Don't forget that this problem that you making the decision of X first, and with the decision of X, you will know the exact value of C, A, and B later, right? Once you know the value of C, okay, you can have an uncertainty of C transpose X, okay, but their expectation can be represented as replacing each element in the C vector as their expected value, okay. And then with the decision of X, okay, cause, like last lecture that we keep saying that, cause the uncertain condition that we can balance the equation A times X equal to B. So with this additional variable of U minus V, okay, and with this corresponding cost coefficient, okay, we will be able to express the original uncertain of A and B as, if suppose that you estimate in a finite situation case, okay, finite number of scenario, okay, we still can maintain this as a linear programming problem. Okay, can you see the relationship now, okay, between Danzig's paper here, okay. So he used this first example, okay, to illustrate the way to handle the uncertainty for the coefficient of the objective function, okay. And now we move to the second example. He using this example to express about the shipping to an outlet to meet an uncertain demand. Okay, now he said this one dealing with demand. Normally the amount of demand represent on the right hand side of the linear programming model. Okay, the problem is stated on the screen that let us consider a simple two-stage case. A factory have 100 items on hand and may be shipped to an outlet at the cost of $1 a piece to meet an uncertain demand D sub 2. In the event that the demand should exceed the supply, this necessarily meet the unsatisfied demand by purchases on the local market price at $2 a piece. Therefore, the system equation based upon this situation can be represented as a set of equation in number 4 here. Okay. The first equation in the set equation number 4 is 100. Certainly, you know that 100 item is is what you already have. It's the available number of this item that we have in our factory, equal to x sub 1 1 plus x sub 1 2. What is x sub 1 1? X sub 1 1 is number shifted from the factory, which means that, okay, we have 100 item here. This one, x sub 1 1, is the one that the amount that we will send out of this 100 unit, okay, to the customer. X sub 1 2 is number stored at the factory. This one is that you might not send all 100 units to your customer. Okay, there will be some remaining inventory or safety stock that keep in your factory. That's represented as x sub 1 2. Okay, that's the equation on the supply side. Okay, 100 supply is equal to the one that we ship to the customer plus the safety stock or inventory on hand that we need to keep. Okay, let's look at the second equation here. Okay, for the system of equation 4 here. D sub 2 equal to x sub 1 1 plus x sub 2 1 minus x sub 2 2. Let me hint you a little bit that x sub 2 1 and x sub 2 2 is like u minus v here. Okay, that in the metric form that we show previously. D sub 2 is that the demand, the amount of demand that customer want, which we don't know. This is according to the problem that uncertain demand D sub 2. We don't know here. Certainly, to meet the requirement of customer, you need x sub 1 1 because this is the amount that we send to hopefully meet the demand. But we don't know what is the real demand is. So x sub 1 1 need to make a decision first with x sub 1 2. Okay. For example, x sub 1 1, I'm going to ship 80 items to the customer, and we keep 20 items, okay, on hand. Okay, so you know that 80 items will be sent to customer, okay, but we still don't know how much customer want. Okay, so this amount of 80 unit might be able to fulfill exactly. Suppose that the demand come out 80. Oh, very good. This is how much you want. We ship it exactly what you want. But suppose that the demand is only 70. Okay, we ship it out. X sub 1 1 is 80, but the demand is 70. So you need minus x sub 2 2 here. X sub 2 2 is that, okay, since you ship 80, x sub 2 2 maybe it exceeds the demand. Okay, you might need to carry it back or anything. Okay, but the problem that related to the cost in the model is that this one, it is necessary to meet the unsatisfied demand by purchases on the local market at $2 a piece, which means that suppose that you x sub 1 1, as I told you, is 80. Suppose d sub 2 is 90, not 70 as the previous example. D sub 2 is 90. If d sub 2 is 90, x sub 1 1 is only 80. Therefore, you need x sub 2 1 because it's not enough. 80 unit, you need 10 more. X sub 2 1 will be another 10 in order to balance this equation. You see that this one, x sub 1 1 in D2 is the one that is like ax equal b in the model. This one is like u and v plus u minus v. Okay, but at that time the notation of u v is still not very popular. Is way back 1955. This is how Danzig used to explain the model. And the total cost here, he didn't use the C SU here. Okay, he used the capital C here. You know that x sub 1 1 have a $1 a piece, a cost, the shipping cost. And then if x sub 1 1 cannot satisfy D2, okay, so you need 2 more units here. 2 times x sub 2 1. Okay, because this one is the add up to meet the demand, and you need to find from the local market at $2 a piece. Okay. So this is the model here, but the key problem is that we don't know what is D sub 2 is. D sub 2 is uncertain demand. Suppose we give it briefly, very nicely. Suppose D sub 2 is between 70 to 90. At least 70 unit, at most 90 unit. Okay, and it's in the discrete case, there can be 21 alternatives, right? From 70, 71, 72, 73 up to 90. There'll be 21 alternatives. Okay, for each alternative here or scenario, right? I'm gonna take the word switch it out, alternative or scenario. Okay, for each scenario of D sub 2, which is 21 possible scenario, you will get different value of x sub 2 1 and x sub 2 2. Depend on what is the D sub 2 can be. Okay, and in each case, okay, certainly you lose another $2 for x sub 2 1. But in reality, excuse me, in reality, x sub 2 1 can happen only one scenario will happen, but we don't know. But you know that there are 21 possible scenarios. Therefore, if you consider D sub 2 listed this constraint for all possible case, you will have this equation 21 scenario with x sub 2 1 and x sub 2 2 add for another, each of them have 21 number of variable corresponding to each scenario. Okay, and in this case there is no cost related to x sub 2 2 that you might disagree that x sub 2 2 might be the cost of transportation back to keep it in the factory, or the inventory cost, whatever you want to call it. Okay, but in this case the related cost is only that if you don't meet the demand, okay, which means that the supply is less than demand, you need to buy from the local market, and in this case definitely the infinite amount, there's no limitation for the local market. Okay, you need these two more. So therefore in the objective function here, okay, if you put all 21 possible scenario here for the equation of D sub 2 equal to x sub 1 1 plus x sub 2 1 minus x sub 2 2, therefore in the objective function you will have 2 times x sub 2 1, and certainly x sub 2 1 have another 21 additional variable corresponding to each situation. Therefore the objective function, is it going to be 2 times x sub 2 1 first scenario plus x sub 2 1 second scenario until x sub 2 1 at scenario 21? The answer is no, because as I told you that in reality only one situation will happen. Therefore the objective coefficient of 2 here need to be the average. Okay, certainly $2 a piece. Okay, but for each scenario, okay, the expected cost have to be 2 divided by 21. Suppose that in this case we assume what we call the uniform distribution of D sub 2 within the range of 70 to 90. Okay, so this one have to be the average case. And when you accumulate all possible x sub 2 1 in all case, okay, times 2, okay, you need to find the average. Okay, the 21 scenario, you divide it by 21. And certainly this is the case where you assume that for all scenarios there's the same probability of occurrence. But if they have a different probability distribution, the expected cost need to calculate according to the distribution of those random uncertain parameter here. Okay, but in this case it's more difficult, okay, to consider if D sub 2, as I told you, D sub 2 is between 70 to 90. Suppose this is not a discrete product, like you count 70, 71, 72 pieces or whatever. Suppose this is a liquid. D sub 2 can be between 70 lit to 90 lit. Okay, so therefore it can be any value, not only discrete part. It can be 70 plus 5, 70 plus 512, 513, whatever, depend on how accurate your measuring unit or how precise your measuring unit is used. Okay, even though you measure it up like 72.25, and the other lot of the product also 72.25, because of the accuracy is only the 2 digit for the measuring device, it's not guaranteed that those two value is equal also, because it might be differentiate on the 3rd digit, 4th digit, when your measuring machine is not does not have precision to measure that. Okay, that's what we call the continuous random variable or continuous uncertain case. Suppose D2 have an uncertain case, like can be any value between 70 to 90 and not the discrete value, it's a continuous value. Therefore, this equation lead you to what we call linear programming in infinite space, not the finite space, because all the D2 is the uncountable, the infinite number of possible of D2 lead to the infinite number of x up to 1 and x up to 2 additional value for each scenario, and the number of constraints is unlimited. Therefore, with the number of variable also unlimited, it go to another dimension of a very large scale linear programming. Now you have uncountable number of variable and uncountable number of constraint and equation. Okay, but certainly if you want to maintain the way you're going to use what we call the simplex based method or other method for linear programming in the finite space, okay, you need to approximate it. Okay, or in engineering sense we call the discretization. Discretization is mean that we try to approximate the continuous case, continuous domain space, whatever, okay, to a finite domain space. Okay, okay, this one we express the detail of these two examples from the paper of Danzig. Okay, to be able to illustrate and give you more sense. Okay, in the next section I will give you some of the other example and show you in a much more detail. Okay, hope you continue watching. Okay, from this moment, okay, see you later in the next script. Thank you.